Hello, my name is Jack John. I'm from Intel. I'm cloud system architect. Today, welcome to my session. Today, I'm going to talk about our project called Mediumware Smart Starter Engine, MASSé agenda. We're going to have a high-level introduction about the MASSé, how it works, and what it's going to solve, what problem it's going to solve. So basically, the MASSé focused on tier storage. Optane plus QLC. Optane means Optane SSD or Optane PMAN. We're going to show you the test data, evaluation data, show how it's achieving our goal. And then we'll update you the status, and then what's we're going to do next. So MASSé, Mediumware Smart Storage Engine. On the high level, we will see why we need MASSé, right? On the left side is typical of software stack. I mean, a very simplified one. User space, you have application, and then you go through file system, and then talk to NVMe driver and manage the drive, right? Typically, we see a couple of the issues or challenge from customer in the past 4 or 5 years, especially for 3D cross-point. So one typical question that people ask, say I have something application, I replace the QLC SSDs with the Optane SSDs, but we haven't seen any great performance in benefit. We can see 20%, something 50% or 30%, but really we are not achieving that. Compared to cost, it's not reaching our goal. While the medium itself is like, we can see the 3D cross point versus the NAND, you can easily to see from the medium itself, it's like 100 times better. But we're not seeing that in the application level. And then the second challenge is, for the recent years, we have QLC SSDs. The purpose of that is to dramatically reduce the cost, but they have the large capacity drives, so that forced the SSD designer the former need to be using large IO table, which is 16K or 64K. You can easily see that 8 terabytes, 16 terabytes, 32 terabytes, they have to use 64K IO table. While traditional, current application, they all align 4K. In order to better utilize those QLC SSDs, you have to change application by application. So the challenge is who's going to do this investment for this change. That's why we put called MASSé, a piece of lightweight software just under application in the user space. We bypass file system and directly manage the drive. I mean, the either Optane SSD or NAND SSDs. Basically, they understand which medium inside the SSDs and doing different data structure and placing data differently. So one basic thing like 3D cross-point, we don't need the erase and program before programming. It's right in place. While the QLC SSDs, we merge data in, I'll talk in next section, next slides, couple of slides. We basically sequential write data to the SSDs. So different data structure, different data placement. The purpose is for that is to maximize hardware utilization. Okay, we're top level, in hardware level, we can see, give you a quick view of this. So basically the engine is configurable. So configurable means the ratio of the drives can be configurable, pre-configurable actually. See on the left side, you have one system, which is typical. I have like 12 drives, 5 Optane, 5 QLC. On the right side, when this engine up, this is just example. We got 5 engine up. I call it good, better, best. Good is like really intensive, very cost saving, so all QLCs, and then the best is like all Optanes, which is high performance, but cost is high. And then you have different ratio Optane plus QLC, so make a balance for performance and cost. The software side, I mean, inside the box, actually, if you look at this, under the hood, NVMe driver, we're not changing. The Optane and SSDs firmware not changing. The same, operate the same thing, same way as typical. In this small software box, we have volume tier, which means volume means we control single layer drives, all Optanes or TLCs, just one layer, and tiers, which means we have 2 layers, fast plus slow Optane plus QLC. We have mapping table. This is a very important part. You can look at it. This is similar to kind of out to P table. Since we sequential write to the drive, there's no garbage collection in the drive, I mean SSDs. So basically we can see that P, physical address, very close to the logic address. Our 7 days continuous 4K random write test shows the internal, if you look at the log table, smart log, the SSD have the WF is 1.057. This means there's no data relocation. So basically in that, you can see that there's no data relocation means the address to look at it is pretty much the physical address. And then since we sequential write, we have GC manager, we have to GC at some point. Basically we need relocate the data. And then we use KV hash table, use hash table to manage the drive. We use KV key value store to manage the drive as well, the block. We have telemetry, we have workload pattern, AI engine. Basically, we learn every workload go through this engine, so we can kind of through time to learn the workload. The purpose for that is going to be smart replacing the data, placing data smartly. On the top, we have those 2, telemetry and workload engine is under development. It's not available right now. Key value, the interface for we have key value, and then we have virtual file system. We have virtual blocks. So basically you can interface file system like ES4, we can replace that with abstract file system. We call it FS. And also we can present the host with present to the application with the block interface. Quick talk about this. This multi-tier storage and the means architecture. Remember we have volume and tiered. This is tiered. On the DRAM, we have hashing table. Basically all the mapping table is here. We have hashing tree, the pointer, the entry on the disk. We have say 8 bytes of there. And then in the second and third is Optane QLC. Optane have, besides temporary data, we also have MAC data. We have something called segment. Segment has all the MAC data. You can look at segment is combined with the MAC data and data. MAC data area is also another segment that is MAC data, MAC data. It's kind of, the QLC is only data. Quick view of because Optane is really expensive. We're trying to use 2 to 3% of the total storage. We only put Optane in the right path because that can maximize this Optane 30-point utilization. So basically, in very short, not even all, but in short, all the small chunk going to merge in the DRAM. While it merging, the small chunk going to persist to the Optane first. Once it persists, it come back to the host and say the right time. While the actual data is not flashing to the QLC yet. Since we commit every small chunk, the write performance is very close to Optane SSD, also the QoS, close to Optane SSD or perfor-mance performance, which is we maximize the performance of Optane. Since we persist, we don't worry about the, by the way, we're going to have merge those data to large chunk. Here is 256K, and then sequential write to QLC. Since we already persist the small chunk to Optane, we don't need to worry about data loss, power loss. So data always can be recovered. So actually, if you look at this, it's basically Optane as a power loss protection and also help the QLC to merge the data, large chunk of data. On the storage side, we have we divided whole, QLC or TLC and SSDs with something called L band, or you can look at that. This is eraser band. So basically within that band, we put a segment. We use segment concept. We have, this is circular buffer. We have a header found to the header pointer and tail pointer. When you write, always write to the tail pointer. When you get collection data, data replication, we read from top to get valid data, read out, and then that's part. We have 3 parts to improve our concept and give the performance data. So first, MASSé versus RocksDB, and then also MASSé versus the using MASSé and check all different kinds of medium performance. And then last one, we have case study with TeraDB, balanced TeraDB. TeraDB, you can look at that with enhanced RocksDB. MASSé versus RocksDB, I see if without the MASSé, the RocksDB, P4800X, which is Optane, versus P4510 TLC, you won't see much difference, only 10%, 12%. Again, this is DB bench test, 50-50 read and write, random. And then once we replace the MASSé, replace RocksDB with the MASSé, you can see same drive P4800X, you can see 60% operation per second improved. And the best part, if you see look at the read QS, we can achieve like at least 40 times from 2.9 to 4.9 tail latency. This is huge improvement. We also test a different medium with this MASSé for the same thing, 50-50 read and write. We have 4K, kind of 4K to close the FL test. You can see the read latency QS, we can limit that to 1 millisecond for 3.9. This is huge change, because if you look at FL test with the TLC, QLC, whatever, and SSDs, when the gap collection kick in, the read latency, the tail latency will super unpredictable. This is good, big achievement. Not going to all the data, but then the last part we use V file, virtual file, replace ESD4 file system in the Binance TeraDB environment. So basically, MASSé replacing the ESD4 file system, and you can see we can easily achieve this is DB bench test with 7030. You can see we can easily, just replacing the file system, we can achieve like 2 times better, both OP per second as well as the QS. This is 2.9, 3.9, 4.9. Easily get 2 times better. What comes next? So basically, conclusion is MASSé is proved to be a high performance, effective storage solution that can release the medium capability. Trying to avoid some weakness on the QLC by sequential write data and maximize 3D cross-point SSD, 3D cross-point medium performance. And then combine the 2 with tier storage, fast Optane plus QLC, we can achieve both performance as well as the cost down goals. Our next, we'll design some standard library and user space module for this, especially for standardized WAV file system and WAV block. Currently working on trying to replacing EST4 file system, SFF file system under RocksDB. So we can, without changing anything on the RocksDB side, we can provide the database service with better performance, O plus Q. And then we have MASSé already released 1.0. This is private GitHub, but if you are interested, email me. I can give you access to this private GitHub. Forgot to say this. From day one of this project, we're going to have this open source. This will not keep that. We'll keep this as open source project. So in the next couple of months, I'll push out to the open source so everybody can look at it and to see if it can benefit your application perform your works. We have a white paper at Intel IDZ, Intel Developer Zoom. So you can I talk here and data here. We have that in that paper, so you can take a look at it. And with that, thank you so much. Really for time to attend my session, and your feedback is very important to us and also to SNIA. Thank you very much. Send me any questions.